Good evening, ladies and gentlemen, and welcome to the University of Toronto. My name's Alison Keith, and I'm the director of the Jackman Humanities Institute in the Faculty of Arts and Science at the University of Toronto. Before we begin, I wish to acknowledge that we're gathered on unceded land that remains a sacred gathering place for many peoples of Turtle Island. It's the territory of the Huron-Wendat and Petun First Nations, the Seneca, and most recently, the Mississaugas of the Credit River. I ask you to join me in acknowledging these communities, their elders, both past and present, as well as future generations. The Jackman Humanities Institute also acknowledges that it was founded upon exclusions and erasures of many Indigenous peoples, including those on whose land this institution is located. It's my pleasure to welcome you to the 2022 Wiegand Memorial Foundation Lecture. This lecture series was established to honor the memory of the late Dr. William Wiegand. Dr. Wiegand was an alumnus of the University of Toronto who won international acclaim for his pioneering work in the science of rubber compounds. And then, as a second act, he immersed himself in the study of theology and classics. At U of T, Dr. Wiegand earned a BSc in chemistry and a master's in physics. Later, he added a Master of Arts in Greek from Columbia University and an honorary doctorate of laws from the University of Toronto. As the breadth of these qualifications suggests, Dr. Wiegand was deeply interested in how scientists and philosophers approach some of the larger questions confronting humanity today, particularly the issues that arise from a dialogue between science and faith. To honor his memory, Dr. Wiegand's family set up a foundation, which then in turn established this lecture series. Past speakers include such illustrious thinkers as Northrop Frye, Alan Bloom, Margaret Atwood, Robertson Davies, Sir John Eccles, and Ronald Numbers. Dr. Wiegand had an unshakable belief in the need for open dialogue between science, faith, and spirituality in the modern world, a belief that we in the Faculty of Arts and Science share. It's an honor for the university to be involved in this series. And on behalf of the Faculty of Arts and Sciences, I'd like to express our gratitude to the Wiegand family for making it possible for us to host these lectures. I'd also like to thank the members of the Wiegand family and the Wiegand Memorial Foundation for joining us this evening. A few housekeeping details before I introduce tonight's speaker. The lecture's being live streamed and recorded, and so it will be available for viewing after this evening as well. And the Q&A will be moderated by Bree Lohman, a doctoral candidate in the Institute for the History and Philosophy of Science and Technology. She will join our speaker at the table after the talk. This year's speaker is Professor Alexander Jones, Leon Levy Director of the NYU Institute for the Study of the Ancient World, and professor of the history of the exact sciences in antiquity there. Professor Jones studied classics at the University of British Columbia and the history of the ancient mathematical sciences at Brown University. Before going to NYU, he was on the faculty at the University of Toronto for 14 years, and it's a pleasure to welcome our colleague back this evening. His work centers on the history and transmission of the mathematical sciences, especially astronomy. Recent books include Mathematics, Metrology, and Model Contracts, a codex from late antique business education, and A Portable Cosmos, revealing the Antikythera Mechanism, scientific wonder of the ancient world. He's also the author of several editions of Greek scientific texts. His current research interests include the contacts between Babylonian and Greco-Roman astronomy and astrology, and the Antikythera Mechanism and other artifacts of Hellenistic and Roman period astronomy, about which we will hear much more this evening. And so without further ado, his talk tonight is entitled Bronze Gears and Ethereal Spheres, the Antikythera Mechanism and Ancient Greek Cosmology. Please join me in welcoming Professor Alexander Jones.
Thank you very much, Allison. Is the mic working well for me? Great. Okay, and it's a great honor for me to be invited back to what was for many years, more than the 14, because I was a postdoc at IHPSC for several years before that, but to be invited back in this lectureship, which is such a distinguished roster of people who have given the lectures in the past. So without further ado, I'll dive straight in. So among the front page stories in the morning newspapers of Athens on November 6, 1900, was a curious report that the Minister of Education, Spiridon Stais, had a meeting with the Professor of Archaeology of the University of Athens, who had approached the minister on behalf of a group of sponge divers from the island of Symi. The divers claimed that they had found ancient bronze statues on the seabed near Cape Malea at the southeast tip of the Peloponnese, and they were offering to help recover them for the Greek government, if the government would provide the means for raising and transporting the heavy objects, as well as remunerating the divers commensurately with their value. The Minister of Education consulted the Minister of the Navy and the head of the Archaeological Service. The archaeologists quickly realized that the divers had found a shipwreck from Greco-Roman antiquity, the remains of a ship laden with works of art. 2 days after that first meeting, an agreement was drawn up that a Navy vessel carrying a delegation of archaeologists would accompany the divers to the site and investigate the situation. No time was lost. On November 23rd, according to the Julian calendar that was in use in Greece at that time, equivalent to December 6th Gregorian, the transport ship Mycale set out from Piraeus in company with the sponge divers' 2 small boats. It seems that it was only at this point that the divers revealed the actual site of their discovery, not the straits between Cape Malea and Kythera, as they had previously been saying, but off the northeast coast of the tiny island of Antikythera, which was at that date the southernmost part of the Kingdom of Greece. The spot was, according to the divers, at a depth of 35 fathoms, or more than 60 meters, and at any season, let alone in December, the waters of Antikythera are too rough for diving on most days, even with today's equipment, to say nothing of the brass helmet and hose suits used by the sponge divers of a century ago. Nevertheless, within a few days of their arrival, a 3-hour window of calm weather allowed the divers to descend for brief, maximum 5-minute turns on the seabed to identify salvage-worthy artifacts and prepare them for being raised to the surface. Among this first haul were 2 headless marble statues, smaller fragments of several marble and bronze statues, various ceramics, a bronze sword, and the complete and striking head of a bronze statue that was initially thought to represent a boxer, but after conservation has been known as the Antikythera philosopher. I would make no comment about how one can confuse boxers and philosophers, but there we are. It was decided to stay on at Antikythera, and what started out as an exploratory investigation was prolonged into a 9-month campaign of salvage that was only wound down in September 1901, when it appeared that the divers had recovered every significant artifact accessible to them. From the outset, the principal motivation for this pioneering but very expensive effort in submarine archaeology had been the statuary. But from that point of view, the results were not entirely satisfactory. The many marble statues, among them larger-than-life figures from epic and myth and a set of colossal horses, had been mutilated by the sea life that had accreted to them, except where they had been protected by the mud of the seabed. There were a few more or less intact bronze statuettes, but the larger bronzes were all in fragments, and only one, the so-called Antikythera ephebe, or youth, could be reassembled with some approach to completeness. One of the reasons that the laborers were allowed to continue through the summer of 1901, despite the tapering off of exciting finds, was the hope that more missing pieces, especially of the ephebe, would emerge. Work on reconstructing the ephebe began in the National Archaeological Museum already in 1901, and a space was reserved in the museum for nondescript bits of bronze that might turn out to be pieces of the puzzle. Spiridon Stais, the Minister of Education whose vision and initiative had made the operations at Antikythera possible, left office when the government of Georgios Theotokis fell in November 1901 following the so-called Gospel riots, but he maintained a personal interest in the finds. So it's not surprising that on a visit to the museum the following May, he was shown the room with the miscellaneous bronze bits. What is surprising is that apparently he was the first person to notice among them 2 or 3 that certainly did not come from a statue, but whose faces exhibited toothed gear wheels and tiny and scarcely legible inscribed writing. Again, the Athens newspapers quickly got wind of the former minister's strange discovery, and for days afterwards they followed the debates among local archaeologists and assorted experts about what this thing could have been and what it was doing on the ill-fated ancient ship. Particular efforts were made to read the inscribed texts, and although at this point the yield was less than 50 Greek letters, they included apparent references to the sun and the planet Venus, suggesting that this was some kind of astronomical device. On the other hand, since it was on board a ship, there was a general consensus that it was somehow part of the ship's gear and had a nautical application. Otherwise, the disputation generated more heat than light, and when things had calmed down, the heavily corroded and extremely fragile fragments were put in the queue for cleaning and conservation. Thanks to the enthusiasm of the Greek press for all things archaeological, the episode was very much in the public eye in Greece, but not so abroad. I found only one tiny article mentioning the discovery in the London Standard for June 7th, 1902, which was picked up by a few other British papers. The cumulative bursts of research through which we now have a very solid understanding of the device began with Derek de Solla Price, an Anglo-American historian of science whose specialty was the history of clockwork mechanism. This subject traditionally was considered to have its start in the Middle Ages, so Price was naturally intrigued to learn from the rather limited published materials available in the early 1950s concerning the fragments that there existed some kind of a complex gearwork device from ancient Greece. Thanks to a 10-day visit to the museum in late 1958, Price arrived at several crucial insights that became the foundation for his own and all subsequent work on the device, to which he also gave the name that has stuck, the Antikythera Mechanism. He was the first to deduce the general appearance and structure of the mechanism as a box with faces of bronze plate on both front and back, the other sides being wooden. Both the front and back faces featured displayed dials with revolving pointers constituting the outputs of the device, while the input motion was by means of a knob or crank on one of the sides. Price also established the main strategies for studying the fragments that have been followed since. Thus, he grasped that one of the principal steps towards identifying what each of the various outputs meant was to determine for each surviving gear how many teeth it had on its perimeter and how it connected with the other gears. Since many gears were known to be hidden inside the fragments, he saw that radiography had the potential to be a powerful tool for acquiring this evidence. For this, he had to wait until the early 1970s, when it was first technically possible to make X-ray radiographs of the fragments in the museum. The next investigators to make close study of the fragments in the late 1980s and early 1990s were Alan Bromley and Michael Wright, respectively a historian of early computers and a curator with expertise in early scientific instruments and mechanisms. In addition to direct examination and conventional radiography, Wright and Bromley applied radiographic techniques designed to yield information about the location of internal features in 3 dimensions, in particular linear tomography. Most recently, in 2005, the fragments were subjected to high-resolution X-ray computed tomography and reflectance transformation imaging, a technology based on multiple digital photographs. Sorry, I didn't want to go ahead. Multiple digital photographs that allows one to manipulate reflectance properties of a surface to highlight fine details such as faint inscriptions. This campaign was conducted by the Antikythera Mechanism Research Project, or AMRP, a large collaboration of academic scholars, technical experts, and curators of the museum. As studied in 2005, And as one can see them now in the galleries of bronzes in the National Archaeological Museum in Athens, there are 82 identified fragments of the mechanism, ranging from the largest fragment called A, with dimensions just 16.5 by 17.5 by 5 centimeters, which contains most of the surviving gears and interior mechanical elements, down to tiny flakes of plate that may preserve traces of 1 or 2 inscribed Greek letters. Most of this profusion of small fragments resulted from conservation work done on the larger fragments in the early 20th century. The fragments are almost entirely composed of brittle corrosion products of bronze, with scarcely any free metal surviving. Only museum staff are now allowed to touch them, let alone handle them, as we saw Derek Price doing in the 1958 photograph. Every time I see the fragments when I visit the museum, I experience surprise at how small they are. Photographs and images seen on a computer screen do not convey the delicacy of the visible gearwork and the tininess of the inscribed lettering, some of it comparable in size to the writing on intaglios and coins. Yet there is so much complexity, so much information in the fragments. The tomography from 2005 brings this out stunningly. As you can see from this video, find how to start it. There we go. This video, which was composed of successive tomographic slices of fragment A, starting from its front face, the one featuring the big cross-spoked gear that one usually sees in photos, and ending with the back face, where one gets a fleeting glimpse of the inscribed exterior plate. The whole journey covers a space of less than 3 centimeters. And here, in a conventional photograph, is just the lower right corner of the back face of the same fragment A, on which one can see parts of 2 dials with short inscriptions on their scales, a continuous text inscribed in the irregularly spaced shape around the larger dial, and overlying the dial plate, a layer of corrosion products that preserves the mirror reversed impress of another plate that bore yet another continuous text. The biggest lettering here averages about 2 millimeters height. These drawings give a general idea of how we believe the mechanism must have looked. Box-shaped with front and back dial faces of metal plate, dimensions roughly 30 centimeters by 17 centimeters, and the other faces wooden. The total front to back dimension isn't certain, but must have been somewhere around 10 or 12 centimeters. A knob or crank on the right side drove the gearwork, thus setting the various dial pointers in motion. Turning the knob clockwise represented going forward in time at a highly accelerated rate of roughly 1 year every 5 turns. The outputs on the dials represented either various ways of measuring out time or various things happening in time. The general layout is not radically unlike Price's 1974 drawing, though there are some important differences. In particular, the 2 large dials on the back, which Price, like everyone before him, had thought were composed of concentric rings that might have been mobile, are in fact spirals, as Michael Wright brilliantly deduced, despite the almost complete loss of the left half of the dial plate. Wright also was the first to identify the correct function and original location of the disc-like feature in the middle of the front dial, which is mostly extant but displaced in fragment C. And here is a schematic diagram of the gearwork as it was reconstructed more or less definitively in 2006 and 2008 in AMRP papers published in Nature. I say reconstructed, but the fact is that 27 of the gears shown still exist, in whole or in part, in their original locations in fragment A. And we now have enough evidence between the physical remains and the dial inscriptions to leave no doubt about the few totally lost gears that have to be conjectured to complete the structure. They're the ones that are in white instead of gray on this diagram. As you see, almost all the gears are oriented in the same way, parallel to the dial plates. And for the most part, they are connected either by being mounted on the same axle or by being adjacent so that the teeth of one drive the teeth of its neighbor. The gears form multiple chains that branch out from the one labeled A1, which is the input drive from the knob on the right side, eventually emerging through the front or back dial plate to turn one or another of the dial pointers. This fully reconstructed system of gears drove all the pointers of the 5 dials on the back face, as well as multiple outputs on the single front dial. What I would like you to keep in mind is that we are quite sure that we have essentially complete knowledge of the back face and its displays from a mechanical and a functional point of view. Whereas for the front, there remain some gaps and uncertainties, in part because the remains of the front are less completely represented in the extant fragments, and because what we have of the front underwent more disturbances while the mechanism was under the sea than what we have of the back. Nonetheless, I'm going to try to convince you that these uncertainties are not quite as extensive as they appeared to be as recently as 2008. I'll take a slightly circuitous route to get there. I began my talk with a recounting of the background of the mechanism's discovery in 1902 and the excitement and debate that ensued in the following weeks. Then I fast-forwarded to Derek Price's work on the fragments in the late 1950s. What about the intervening half-century? By skipping over those years, I didn't mean to imply that the interest in the fragments vanished entirely after 1902, but that Price's advances scarcely depended on anything that had been done before. In fact, he had a predecessor whose acute observations and insightful ideas about the fragments make fascinating reading to a present-day student of the mechanism, but had little influence on subsequent research because he never published them. Albert Rehm was a young German classical scholar who happened to have just the combination of attributes to qualify him to study the fragments in the years immediately following their discovery: interest in ancient astronomical instruments and texts, and expertise in Greek epigraphy, the study of inscriptions. He visited the Archaeological Museum to study the fragments 3 times in 1905, 1906, and 1924. And after the first 2 of these visits, he wrote extensive notes and drafts for intended publications that ultimately ended up with his other papers after his death in 1949 in the Bavarian National Library in Munich. Putting together clues from the physical features of the fragments, from what he could read of the inscribed texts, and from his broad knowledge of Greek and Latin literature, Rehm arrived at the conviction that the mechanism had been a planetarium. He had seen a modern clockwork-driven mechanical planetarium at the Herrenchiemsee Palace in Bavaria, a replica of one at Versailles that was made for Louis XV. But of course, this 18th century planetarium has the planets, including the Earth, orbiting the sun, whereas Rehm realized that an ancient Greek planetarium would in all probability show all the heavenly bodies, including the sun, circling around a central and stationary Earth. One of the fragments appeared to contain part of a system of ring-shaped pieces of metal plate, what we now know as parts of the upper spiral dial of the mechanism's back face. Rehm proposed that these apparent rings were originally mobile and turned by the gears, and that each bore a mark representing one of the planets or the sun or moon in the order corresponding to their assumed relative distances from the Earth. When an operator turned the crank, each ring would revolve with the appropriate relative speed for the body that it represented. Derek Price started out with a similar idea that the mechanism was a planetarium, but that was before he had seen the fragments in person. Afterwards, though he deduced that the front dial must have shown the motions of the sun and the moon through the zodiac, he came to the conclusion that the kinds of interconnections of gears that the mechanism employed would not have been capable of representing the motions of the planets in a way that would have been satisfactory according to what the Greeks knew about planets around the time the mechanism was made, which Price believed, probably correctly, to be the early 1st century BCE. He therefore assumed that any output relating to the planets would have had to be of a different kind, not spatial, but temporal, such as marking the stages of their cyclic behavior in time without actually showing that behavior. More generally, he maintained that the mechanism was fundamentally a device about astronomical time, not space, choosing to call it a calendar computer. Incidentally, Price meant this in the sense of an analog computer, a device that employs continuous physical motion to calculate certain specific quantities. In the present day, when the word computer is so strongly associated with programmable digital computers, perpetuating Price's language by applying to the mechanism such expressions as the world's first computer is highly misleading. Now, Michael Wright came to the conviction that while the outputs of the mechanism's back face appeared on the available evidence to fit Price's time cycles. And this has been completely borne out following the AMRP's contributions. Pause while a slide is going to appear. Don't know what happened to that slide. A slide is missing. Anyway, there must have been more to the front dial. Features projecting from the front of fragment A implied that mechanical parts had surely been lost there, and there appeared to be room for something fairly complex. And given that the front dial was already known to have pointers showing the motions of the sun and moon, what could this lost gearwork have plausibly been, other than the completion of a planetarium display? In the absence of specific evidence to determine the details of any of the planetary gearwork, Wright built a proof of concept working model, that's what this slide shows, of a reconstructed Antikythera mechanism with a full planetarium on the front, such that the behavior of the pointers conformed to hypothetical astronomical theories that Wright thought would have been close to the limits of scientific sophistication possible for the Greek astronomy of the mechanism's day. What did the term planet mean to an ancient Greek? To understand that, we need to forget everything we learn in school about the solar system, stars, and galaxies. To an ancient Greek, more or less any luminous object that one could see regularly in a clear sky counted as a star. They came in two varieties. Unwandering or fixed stars were the ones that make up constellations, keeping their configurations relative to each other apparently unchanged, no matter how long one observed them. Most of them had a rising point somewhere on the eastern horizon and a setting point on the western horizon, and they crossed the sky from east to west through part or all of the night. In the northern part of the sky, there were stars that never rose or set, but traced paths circling around a point, the north celestial pole, above the northernmost point of the horizon. A few stars had names in their own right, but most were named according to the constellation they belonged to and where they fitted into the imagined constellation picture. For example, the heart of the lion in the constellation Leo the Lion was the name of the star that now bears the common name Regulus. But there were a few stars that did not keep a fixed position relative to the others, and so were called wandering stars or wanderers, planetes, the word from which we get planet. 5 of them look rather like bright stars, bright fixed stars, and these are in fact planets in our modern sense, specifically the 5 that can be seen without telescopes: Mercury, Venus, Mars, Jupiter, and Saturn. The moon also counted as a wanderer, and so, less intuitively, did the sun, because although normally one would never see the sun and other stars, except the moon, in the sky simultaneously, astronomers understood that there were always stars and constellations up there in the daytime sky, though they were rendered invisible by the sun's dominating light. So sometimes Greek and Roman writers speak of the 7 planets, and sometimes of the 5 planets, depending on whether or not they want to include the sun and moon. We first encounter systematic ways of naming the 5 around the time of Plato, in the 4th century BCE. The more common system named each as the star of one of the Greek gods. So the star of Hermes was our Mercury, the star of Aphrodite was our Venus, the star of Ares, our Mars, and so on. Our modern names are in fact those of the Roman gods that were considered to be the counterparts of the Greek ones. An alternate system named each by a descriptive adjective. So gleamer was Mercury, lightbringer was Venus, fiery one was Mars, and so on. And some writers like to use both systems together, as in gleamer, the star of Hermes. The sun and moon were normally just called by their traditional common names, Helios and Selene, respectively. The wanderer's wandering is not random. Each of them is always located somewhere within a fairly narrow belt in the system of constellations. And again, it was around Plato's time, or not much before, that the Greeks adapted from Babylonian astronomy a division of this belt into 12 sectors named for constellations that roughly coincided with them, the zodiac. Each of the 7 planets has an overall eastward trend through the zodiac. The moon is the fastest, taking a little over 27 days to make a complete round. While the sun takes a year to do so, Mars a little under 2 years, Jupiter about 12 years, and Saturn, the slowest, about 30 years. Both Venus and Mercury take on average exactly the same time as the sun to go around the zodiac. That is 1 year. while alternately running ahead of the sun and so being visible as evening stars, or falling behind and so being visible as morning stars. This fairly basic level of knowledge about the planets could be extended along two lines of inquiry. First, we can advance from this perspective of what an observer in, say, Miletus or Athens or Rhodes sees, namely various bright spots gradually moving around up there among the constellations, to a more spatial conception of where all these objects are, not just in terms of direction from us, but also in terms of distance. And secondly, can we refine our understanding of their wandering movements beyond the simple observation that they all go around the zodiac, though in different overall speeds? So let's look, first of all, at how the Greeks approached the first, more cosmological question. The fixed stars are seen to travel in the sky in the course of a night, following paths that, if they left a trace as in a time-lapse photograph, would appear as circular arcs, with the north celestial pole as their common center. They behave exactly as if they lie on an otherwise invisible spherical surface or shell that spins around the Earth on an axis, of which the north celestial pole is one end, while the other end, the south celestial pole, has to be imagined as below the southernmost point of the horizon. Constellations don't seem to get bigger or smaller as they revolve around us, or as we travel from place to place. So the Earth must be right at the center of this celestial sphere. And the celestial sphere must be immensely large, so large that the Earth can be treated as a geometrical point in relation to it. But the Greeks knew powerful arguments that the Earth, too, had curvature in both the north-south and east-west directions, and indeed was itself a sphere. Among the evidence were the facts that the north celestial pole gets higher above the horizon as one travels north, that eclipses of the moon are seen at different local times of night at different localities, and that the shaded part of the moon in an eclipse, understood by the Greeks as the Earth's shadow, has a convex arc-shaped outline. Hence, by about 400 BCE, mainstream Greek thinking about the structure of the cosmos incorporated this two-sphere framework of a minuscule spherical Earth stationary at the precise center of a vast revolving celestial sphere that was rendered visible only by the stars embedded in its surface. The celestial sphere was a powerful concept in a scientific sense, since it provided a mathematically tractable frame of reference for cataloging the system of constellations, for investigating astronomical problems such as the seasonal variations in the lengths of days and nights through the year, and much else. It was also a powerful image that came to be widespread in visual culture, sometimes represented with the constellation pictures, as on the globe of the Roman period Farnese Atlas, more often with circles drawn on its surface, such as the celestial tropics and equator that related to its applications in astronomical theory. The iconography of philosophers and astronomers often portrayed the sage with a model globe. And how do the wanderers fit into this framework? I just mentioned that one of the considerations contributing to the belief in a spherical Earth was the supposition that lunar eclipses are occasions when the Earth's shadow, cast by the sun's light, falls upon the moon. This was part of a broader understanding, which emerged in the 5th century BCE, of the moon as a spherical body that is not luminous in its own right. Instead, what we see is the part of the moon's surface that is illuminated by the sun. This hypothesis provided a satisfactory explanation of the basic phenomena of the moon's phases, as well as both lunar and solar eclipses. The sun might as well be assumed to be spherical too, if only on analogy with all these other spheres. Now, the moon must be closer to us than the sun if solar eclipses are caused by its obstructing the sun's light, and it must be closer than the fixed stars and planets, since every once in a while one of them can be seen to disappear as if behind the moon, as the moon makes its relatively fast motion through the zodiac. But how much closer? Here, the explanation of the moon's phases turned out to have a crucial consequence. Half-moon phase, when the visible part of the moon's disk looks like a half circle, delimited by a straight line, always takes place around halfway between the new moon and full moon phases, when the moon stands about 90 degrees from the sun in the sky. That can only be if the sun is much further from the Earth than the moon is, so that the triangle having the Earth, moon, and sun as its vertices can have a right angle at the moon because of the half-moon phase, and nearly a right angle at the Earth. For example, Aristarchus of Samos in the 3rd century BCE assumed that the angle at the Earth at half-moon was, as we would express it, 87 degrees, and showed that if so, the sun must be about 19 times as far as the moon is from the Earth. This was a huge underestimate of the ratio, which is in fact around 400 to 1. But even with 19 to 1, we have to start thinking of the celestial part of the cosmos, the home of the stars and the planets, as being a truly three-dimensional space, like an almost solid sphere with just a tiny bubble in the middle where the Earth and the surrounding air are. Meanwhile, now that solar eclipses were understood as caused by the moon's shadow falling upon the Earth's surface, the fact that the same solar eclipse appeared differently to observers in different places on the Earth could be seen as an indication that the moon must, after all, not be all that far from the Earth, near enough that in principle one should be able to measure its distance using the size of the Earth as reference. By the later 2nd century BCE, estimates of the moon's distance were getting to the right order of magnitude, in the neighborhood of 60 Earth radii. Since Eratosthenes had shown, again in the 3rd century BCE, how a few basic assumptions and some half-decent geographical and astronomical data could give you a basis for estimating the Earth's size in mundane units of distance, the scale of the cosmos, at least as far out as the sun, could now be quantified in human terms. And where did the 5 planets fit into this cosmology? Aside from knowing that they had to be somewhere beyond the moon, the ancient Greeks lacked any direct observational evidence, such as a sighting of Venus transiting across the sun's disk, that would establish even the order of their relative distances from the Earth. The conventional approach was to correlate distance with speed. Since the closest planet, namely the moon, goes around the zodiac in the shortest time, it seemed reasonable to assume that if one sorted the 7 planets in increasing order of their periods of going around the zodiac, this would put them in increasing order of distance. There remained the problem of how to order the Sun, Venus, and Mercury, since they share the same one-year-long zodiacal period. And in fact, different authors gave different sequences for these 3. The most common being, from innermost to outermost, Venus, Mercury, Sun, and Mercury, Venus, Sun. Perhaps one reason that these 2 orders were preferred is that there was plenty of room between the level of the comparatively nearby moon and the much more distant sun, and well, something ought to occupy it. Plato's Republic contains a narrative episode called The Myth of Air, about a man named Air who died in battle but somehow returned to life some days later, so that he was able to recount what happened to the souls of people between their deaths and their rebirths. There was a place, he said, where the souls were each given a token that decided what their next life would be. And in that place was the spindle of necessity, a rotating rod like the spindles used to spin threads, but made of steel and furnished with a whorl like the whorl of a conventional spindle that gives it an additional moment of inertia. He says, the nature of the whorl was as follows. Its shape was like a whorl here with us, but from what Air said, you have to conceive of it as if inside one large whorl, which is hollow and scooped out right through, another one like it but smaller is inserted, exactly fitting it, just like those jars that fit one inside another, and a third one, and a fourth, and 4 more the same way. You see, there were 8 whorls in all, one inserted inside another, showing their upper lips as circles, but making a continuous back of a single whorl around the shaft, which passed right through the 8th one. He goes on to describe their appearances. And the lip of the biggest whorl was speckled. That of the 7th was brightest. That of the 8th got its color from the 7th shining upon it. That of the 2nd and 5th were very like each other, being yellower than the others. The 3rd one had the whitest color, the 4th was ruddy, and the 6th came in 2nd place in whiteness. It's a bit confusing because he takes them out of order. But we have to imagine the aggregate of these 8 concentric whorls is looking something like this. And the spindle and the whorls, he goes on, are in motion. The entire spindle was turned and spun with one and the same motion, while during the whole thing's revolution, the 7 interior circles revolved slowly in the opposite direction to the whole. The 8th of them went fastest, in 2nd place, and altogether the 2nd and 6th and 5th. The 4th circle went in 3rd place, as it seemed to them, making its round. The 3rd circle was in 4th place, and the 2nd and 5th place. Sorry, that's this. Now, what's all this about? Not a word of this long account is astronomical, but Plato has laid plenty of clues that he clearly expects a reader to catch that make it possible to untangle the riddle. The outermost whorl is speckled and moves together with the spindle. It represents the fixed stars. The innermost eighth whorl, which is also the fastest, gets its color from the seventh shining upon it. So the eighth whorl is the moon, and the seventh is the sun. The fifth and sixth have the same motion as the sun's whorl, and so must be Mercury and Venus, probably in that order, according to what's said about their colors. The fourth ruddy whorl and the third and second, all in decreasing order of speed, are obviously Mars, Jupiter, and Saturn. Because this is a riddle or metaphor and not a literal cosmology, it isn't clear whether the ring-shaped lip of each whorl is meant to stand for the planet itself or for a sort of belt or shell of the cosmos inside which a planet resides. But the image Plato conjures up recalls images of the slightly later Aristotelian cosmology, according to which each of the 7 planets is the visible body borne by one of a series of concentric spherical shells, like the layers of a giant onion, enclosed by the celestial sphere and enclosing the mundane world of earth, air, fire, and water. The most memorable visual examples of this image are from Renaissance European art. For example, the world that God has just created in Giusto de Meneboi's 14th century painting in the baptistry of the Cathedral of Padua. But it certainly goes back to antiquity, even if the copies we have are in medieval manuscripts. For example, this picture of the false pagan cosmology from the Christian topography of the 6th century CE traveler Cosmas Indicopleustes, one of the rare flat earthers in the corpus of Greek literature. These are always highly schematic pictures, typically endowing each shell with about the same thickness and often using the images of the 12 zodiacal constellations to represent the sphere of the fixed stars outermost. They convey the cosmic order, but not the cosmic scale. As you may remember, one of the few partial words that were successfully read from the Antikythera Mechanism's inscriptions during those days in late May 1902, following the discovery of the fragments, was Aphro, apparently the beginning of the word Aphrodite, the Greek goddess associated with the planet Venus. And in 1958, Price and Stamiris felt reasonably confident that the entire name could be read. The presence of an allusion to one planet in one of the mechanism's inscriptions was among the considerations that Michael Wright appealed to in support of his hypothesis that the mechanism incorporated a planetarium. Now, when the fragments were subjected to computed tomographic scanning in 2005, the main hope was that the interior mechanical elements would be revealed with more clarity than before. But it turned out that the CT imaging also brought an immense advance with respect to the inscriptions, making texts that were embedded in the fragments visible for the first time, but also greatly enhancing the legibility of the exposed ones. Take, for example, the text that includes that word Aphrodite. It appears on the back face of the fragment that we call B, and is another part of the same mirror reverse impress of a lost inscribed plate that I have shown before on the back of fragment A. This is a photograph made for Reims in 1905, a terrible photograph, but anyway, which shows the fragment more or less as it had been discovered in the museum 3 years earlier. I've mirror reversed the image so the lettering is the right way around. At first glance, it's hard to see any writing at all. You probably can't see it in the projection. But with a bit of effort, one can make out, if not actually read, letters in 3 areas. The largest one in the lower left is where 47 letters were read in 1902, with just one error. The letters Aphro are here. Now, the fragment was cleaned of patina in the early 1950s, so that when Price and Stamiris saw it, and this is what you would see in the museum now, much more text was visible. So, for example, the whole name, Aphrodite, can be made out. They read 198 letters now over the entire fragment, though perhaps as many as an eighth of their readings have turned out to be incorrect as compared with what we believe we can read now. And there remained so many gaps that it was not possible to get the gist of what the text was saying. The AMRP team's first paper, published in Nature in 2006, included as an appendix a first work-in-progress report of new readings of some of the mechanism's inscriptions, based on the tomography and RTI data. At this stage, the noise-to-signal ratio was intolerably high. Nevertheless, the prospect of making an advance with respect to the inscriptions, comparable to what Michael Wright and the AMRP had achieved with respect to the gearwork, was irresistible, and I joined the AMRP collaboration in the hope of being able to contribute to that task. By 2011, I'd made some headway with the part of the back cover inscription on fragment B, using the CT data. Working with CT on the mechanism's inscriptions is a different experience from reading a manuscript or an inscription in the normal way, because at any time you're viewing only a very thin, flat, planar slice of the object, whereas the surface bearing the inscription is seldom exactly flat, so that what you see is typically a small patch of legible letters surrounded by a blur. Here are a few examples of CT slices of B. Here the letters that toward the top are legible, but not the rest. Here more along the right side and toward the bottom, and here another batch again. With a lot of practice, however, one learns how to navigate the layers. So here's a composite image that combines this is Adobe Photoshop work, that combines the best parts of many layers of a stack of CT slices of fragment B. You can see what a difference the CT makes for legibility. In this region, the inscription is actually, the slide vanished. No, this region with the red. The inscription is actually concealed behind a bit of the original inscribed plate that's still stuck on there, so it's only visible in the CT. What was particularly exciting to me in 2011 was what turned up in this run of 12 lines, which it's now possible to translate like this. Now, in addition to Venus, we have references to Mercury, probably, only the end of the name survives, Mars, Jupiter, and Saturn, using both the god-based and descriptive names. The Sun is in there too, and the order they are mentioned is Mercury, Venus, the Sun, Mars, Jupiter, and Saturn, which was the most common version of the ancient Greek ordering based on presumed distance from the Earth. The Moon should therefore precede Mercury, and in fact, the less well-preserved lines further up do seem to be talking about the Moon. Moreover, one can now see what the text was saying about the 7 planets. Back in his 1974 book, Gears from the Greeks, Price had remarked that the part of the back cover inscription on fragment A appeared to be concerned with explaining the dial and pointer readings on the pair of back dials. Now, this part of the inscription on fragment B turns out to be doing the same for the front dial. And there can be no doubt that it was a planetarium display involving both pointers and to show the locations of the planets in the zodiac, along the scale for the zodiac, and little spheres that revolve through ring-shaped regions to represent the planets themselves within a schematic cosmological moving picture. The description appears to be compatible with either of two reconstructions, either like this, with revolving pointers bearing little spheres for all the planets, or like this, with such a pointer only for the Sun and Moon, whereas the spheres representing the 5 planets are embedded in mobile rings that were made to revolve by the gearwork. This second version, with the mobile rings, is rather like the planetarium that Rame had imagined. In either reconstruction, the Moon is represented by small, half-black, half-white ball that's made to revolve to show the changing phases. The disc-shaped mounting of this phase display at the middle of the dial still exists as part of fragment C, though it went unrecognized until Wright figured out what it was. I mentioned there was another line of inquiry concerning the planets in Greek astronomy that was concerned with apparent irregularities in their motions through the zodiac. Though it's true that each of them has an overall eastward trend, that is, in the opposite direction to the much more rapid spin of the celestial sphere around the Earth, the 5 planets intermittently reverse direction, moving westward for an interval of days before switching back to their prevailing eastward motion. These cycles of forward and backward motion are tied to each planet's configuration relative to the Sun. So, for example, Mars always has its fastest eastward motion when it's lined up with the Sun, and its fastest westward motion when it's diametrically opposite the Sun. This cycle, which is called the synodic cycle of the planet, is separate from the planet's average revolution around the zodiac. And if you ask how long it takes for a planet to complete a whole number of both kinds of period almost exactly, you're looking at intervals that run into hundreds of years. This is where another of the mechanism's inscriptions come into the picture. The fragment called G is part of an inscribed plate that may have served as a kind of cover for the mechanism's front face, as the plate with the back cover inscription may have been for the back face. In its present state, it was reassembled by museum technicians decades ago from numerous small bits of plate that had been stuck on the front of fragment C. Additionally, there exist two smaller pieces of the plate and many separate bits of a layer of corrosion product that preserve the mirror reverse impress of patches of the inscription. Their original locations are outlined in white on this composite CT image. So it's very complex. The redundancy is just as well because the fragments were exceptionally hard to read, but the effort was definitely worth it. The front cover inscription turns out to be all about the cycles of motion of the 5 planets, again taking them in the order Mercury, Venus, Mars, Jupiter, Saturn. Each section begins with a statement of how many years it takes for the planet to complete an approximate whole number of its synodic periods, as well as how many times the planet goes around the zodiac in that time. Then follows a stage-by-stage breakdown of the synodic cycle, giving numbers of days of eastward and westward motion, and of approaching and receding from the sun. In what we can read, there is no direct allusion to the mechanism. But given the context, as an inscription found with the mechanism, one has to see this text as not just a summary of astronomical facts concerning the planets themselves, but also a description of the way the mechanism represented their motion by means of the gearwork driving the front display. The data recoverable from the inscription are not sufficient to make it possible to reconstruct the planetary gearwork, except speculatively, and there have been attempts to do that. But they provide us with a good measure of the level of technological and astronomical sophistication of the device. So, what was it for, and who was it for? Let's begin with the archaeological context. A shipwreck that can now be dated with some precision to the years around 60 BCE. The location and the cargo indicate that the ship was en route from the Aegean Sea to somewhere in the western Mediterranean. And there's reason to believe that it was a mercantile voyage, not, as used to be commonly supposed, a Roman ship laden with plunder from the Greek East. The mechanism itself offers further clues. First of all, now that its functions are well understood, there can be no question of its being a navigational instrument. It was part of the cargo, or a possession of a passenger. Among the time cycle dials on the back face, the big upper spiral dial represents a lunar calendar cycle applied to a regional Greek calendar that was in use in cities in and near Epirus in northwest Greece. That's the shipwreck site, and that's where the calendar was used. Another dial represents the 4-year cycle governing the Pan-Hellenic athletic festivals, such as the Olympic Games. And among the 6 names of festivals inscribed around the dial is the somewhat obscure Na festival of Dodona, in the same region associated with the lunar calendar. I strongly suspect that the mechanism was, in fact, made for someone who lived in that area, and that the ship was heading for the Adriatic when it met its fate off Antikythera. If this is correct, it was probably manufactured not long before the shipwreck, though I should say that this is disputed, and there are some scholars who wish to date the mechanism as far back as the beginning of the 2nd century BCE. Since another minor festival inscribed around the game's dial is the Haliea of Rhodes, there is at least a good possibility that the workshop that made it was on Rhodes. I would characterize the mechanism as a didactic device, an instrument that was intended to accompany and illustrate teaching non-specialist students the elements of astronomy and its applications. One of the interlocutors in Cicero's philosophical dialogue on the nature of the gods mentions that the Stoic philosopher Posidonius had a device that he calls a sphaira, literally a sphere, each turning of which, I'm quoting Cicero here, each turning of which produces the same behavior for the sun and moon and 5 wandering stars that is produced in each day and night. Clearly a kind of planetarium, and perhaps something like the Antikythera Mechanism, maybe even made in the same atelier. And the dialogue happens to be set at a date soon after Cicero returned to Rome in 77 BCE from his youthful travels in the Greek East, during which he had made Posidonius' acquaintance. I think it's likely that Cicero had seen this mechanical sphaira in Posidonius' classroom, and years later he drew on his possibly imperfect recollection of it when he used the idea of mechanically simulated cosmology in 3 of his dialogues as an emblem of the power of reason, whether in the human inventor of the device or in the divine orderliness governing the cosmos itself. What I do not see in Cicero, and I find only very rarely in the various other passages in ancient literature alluding to astronomical mechanisms, and there are quite a few, is an appeal to their existence as evidence that the celestial motions operate through mechanical connection too. When reconstructions of the Antikythera mechanism are made nowadays for public demonstration in science museums, the walls and faces are often transparent, so one can see the operation of the gears. The original mechanism, like ancient automata, was built as a closed, opaque case in which the inner workings were concealed from view, so that the effects that they generate could appear the more astonishing. When Heron of Alexandria designed a water-driven pneumatic apparatus that caused the singing of artificial birds to be interrupted when an artificial owl periodically turned its face in their direction, there was no implication that this is how nature operates. Similarly, when Cicero makes a Stoic speaker in his Dialogue De Republica attribute a sphaira resembling Posidonius's to the Syracusan mathematician Archimedes, while wondering at Archimedes' inventiveness that he had figured out how a single revolution could furnish unequal and diverse courses in unlike motions, there is no hint of what was inside the box, such as might have given rise to the quite un-Stoic thought that all the wonderful coordination of phenomena in the cosmos might be the work of some apparatus analogous to gearwork. I find the most interesting ancient response to astronomical mechanisms in the writings of the astronomer Ptolemy, who lived in Alexandria in the 2nd century CE, 2 centuries or more after the unknown designers and makers of the Antikythera mechanism. In a book that Ptolemy wrote late in life, whose title can be rendered Hypotheses of the Wandering Stars, Ptolemy provides technical descriptions with a lot of geometrical and numerical detail of the system of motions and moving bodies that he believes are responsible for the observable motions of the sun, moon, and planets. Among the reasons that he gives for writing this book is to provide guidance for the practitioners of sphaeropoieia, sphaera making, or as we might say, constructors of planetaria. But he can't help interjecting that he doesn't at all like the sphaeropoieia that is customarily done. For one thing, he says, these devices get the astronomy wrong. As an aside, it might be remarked that even the Antikythera mechanism didn't entirely reflect the best astronomical theory of its own time, and Ptolemy's theory is considerably more advanced and complex. But Ptolemy has a deeper objection. Conventional planetaria show the appearances as we see the heavenly bodies from here on Earth against the backdrop of the stars. But they ought to make visible the underlying causes of those appearances, by which he apparently means the actual motions in 3 dimensions of the heavenly bodies, or even possibly the unseen physical entities up there, in which those motions are embodied. This would be a tall order for even an Archimedes. Ptolemy eventually comes to describe these unseen physical entities. They are bodies composed of ether, the 5th element that Aristotle had proposed as the material of the heavens, in contrast to the volatile 4 elements, earth, water, air, and fire, of which everything below the moon down here with us consists. Ptolemy associates ether with certain attributes. It is eternal, unforced and unresisting in its motion, intellectual, and divine. In other words, the heavens are composed of ideal, eternal, and intelligent living beings. And the visible heavenly bodies are like the foci of these entities' souls, which simply will into their mathematically perfect movements all the invisible ethereal components of their bodies, which taken all together constitute those concentric spherical shells that by now should be familiar to us from the earlier Greek cosmologies that I've been talking about. Hence, any mechanical simulation that human craft might assemble from mundane materials cannot be more than an approximation of the celestial realities, let alone an explanation of how they do what they do. As he writes in another earlier treatise, we see that in the imitations of the celestial motions that we make here on Earth, the intertwining and close order of the spheres in the heavens and their axes is troublesome and hard to achieve in such a way that the motions are not obstructed. Whereas in the heavens, this kind of combination does not make an obstruction in any way or manner. Rather, it isn't appropriate to judge this simplicity of the things in the heavens on the basis of things that appear as simple here where we are. For if we took that viewpoint, none of the things that go on in the heavens would appear to be simple. Not even the unchangingness of the primary motion of the celestial sphere's daily rotation, since this very condition of being the same throughout all time isn't just troublesome to achieve here where we are, but absolutely impossible. We should instead base our judgment on the unchangeableness of the natures and motions in the heavens. For in this way, they will all be manifest as simple, indeed more so than the things that appear simple here with us, since no labor or awkwardness can be conceived of in connection with the revolutions. In short, whatever gap subsisted between what astronomers knew and what an astronomically informed mechanician could mimic in the 1st century BCE had widened by Ptolemy's time into an unbridgeable gulf, so that mechanical causation was less and less a viable contender against the kind of animistic cosmology to which Ptolemy adheres. Meanwhile, the technology of gearwork itself seems to have degenerated in late antiquity. Vanishing slide. It was there a minute ago. Where has it gone? Never mind. Anyway, the technology of gearwork seems to have degenerated in late antiquity to be applied only in rather crude gadgets for keeping track of common time cycles, such as the 7-day week or the lunar day. The cousins of the Antikythera mechanism that did not have the misfortune to be lost in a shipwreck eventually jammed and broke, and the parts were tossed in the melting pot. The complex astronomical mechanisms that eventually reappeared in 14th century Europe in the form of astronomical clocks were a reinvention that had lost sight of their ancient Greek ancestry. Thank you.
Everyone, I'll reintroduce myself. My name is Bree Lohman. I'm a doctoral candidate at the Institute for the History and Philosophy in Science and Technology, and I have the honor to be facilitating the Q&A. So if you have any questions, feel free to raise your hand. I believe we're going to have a microphone stand out as well, but I will use the privilege as facilitator to ask the first question, and I hope you'll forgive me, but I'm going to return to the problematic of the Antikythera mechanism as the world's quote-unquote first computer, because as it turns out, my first encounter with the Antikythera mechanism was at the Computer History Museum. I don't know how many of you are familiar with the institution. It is a repository for all things computing history, at least in the United States. It's located in Mountain View, California, that's a short Google bike ride from Building 42 in the Google Plex campus. Now, I actually called CHM recently. I wanted to ask them, do you have any exhibits on this mechanism still? Now, the original, of course, is located in Athens, Greece, but there is a display at CHM in an exhibit, the main exhibit, entitled Computers, the First 2,000 Years of History, or excuse me, Revolutions, the First 2,000 Years of Computing. And it is, the display is located in the first gallery on calculators. Now, as a historian of computing, I can tell you that situating the Antikythera mechanism within histories of computing and computation frames how we understand the device, and as historians, how we historicize it, viewing it as a tool for research, a tool for measurement, a tool for tabulation, a tool for computation. However, you suggest that it wasn't primarily a research tool, but rather it was used to teach astronomy. I'm wondering if you could say more on that.
Okay, well, I mean, this is one of the unprovables, of course. I mean, there's an awful lot about these fragments that we can say we know. But when it comes to who made it, who used it, what was it for, this is something where we can't say we can prove anything. But I'm looking at primarily at the combination of outputs, basically. And I'm using language from computing, of course, when I talk about input and output, because it really does that. You know, you could say it generates data on the dials, but was the purpose so that you could read that data off and use it, or is the point to show the coordination of various kinds of cosmic and human cycles cyclic behaviors relating all to a common sort of background of flowing time. That's an explanation that I think makes sense of the combination. Whereas if you try to find some kind of an application or a user who would need a combination of things like an eclipse prediction cycle on the lower back dial and a little dial that tells you how to count to 4 for the Olympic Games, it's really hard to see that. I mean, nobody needs that 4-year dial for any practical purpose. Its point is, I think, to bring in certain aspects of social life, very, very Hellenic, by the way. Having a local Greek calendar, which is very much about cities and their place, and then these competitions that are open across the Greek-speaking world in the subsidiary dial. That's social. That's not astronomical. So, and then when you see how ancient people like Cicero talk about it, they're drawing big message lessons out of it. I think the immediate point was not so much the kind of, Cicero's sort of theological kind of understanding, but at a somewhat more basic level, the sort of thing you got in a popularizing textbook on astronomy, and we have one from roughly contemporary with the Shipwreck by Geminus. And it has a lot of overlap in what the chapters cover with what the mechanism shows on its dials. To put it another way, a bit rhetorically, is would anyone talk about one of these medieval astronomical clocks as a computer in its purpose? You can say that, yes, it's doing computing because it shows, along with the flow of time, also things like where Saturn is in the zodiac, but that's not really what it was for.
All right, thank you so much. We will open the floor. Are there any questions? Yes.
I think for the sake of people who are on the webcast, I think it's helpful if you use the mic.
Is this working? Is it doing the job?
Yep.
Okay. So, Alex, I just want to really 2 questions. One is just to be sure that I understood what's going on. I noticed in the very first slide parapegma inscription on what was on the front. Is that correct?
Yes.
Okay. And that later gets associated with fragment G?
No.
Okay.
Fragment G is not the parapegma. The parapegma is about stars, constellations, and their annual rising, etc.
All right. Well, then I think I know why I'm confused. Okay. So maybe this question isn't going anywhere.
I didn't talk about that at all in the talk.
Exactly. So you mean the parapegma inscription?
Yeah.
You didn't?
I did not talk
Exactly.
about
Okay. So, all right. So maybe there is something in the question after all. Although I'm misled because of my confusion about fragment G. So parapegma, well, you and I remember the dissertation we sat on many years ago, right?
Yes.
Which was on parapegmata. And what is that inscription about? Is it calendrical, essentially? And you talk about just now in this
the parapegma inscription?
Yeah, exactly.
What it is it's a list with alphabetical letters indexing each line of the appearances and disappearances of recognizable stars and constellations that basically are an annual cycle.
Okay.
And the way that such a thing would normally be done would be on a stone inscription, you would have some system of pegs to show you where
Exactly.
today is in relation to that.
Parapegmata, yeah.
On the mechanism, the sun pointer is pointing to some point in the zodiac, and there's a little zeta written at that degree, and you look up zeta in the parapegma inscription, it will say something like,
Okay.
Arcturus makes its evening rising.
Okay, okay, good. That helps. Because I couldn't see parapegma, what I understand about them, and how it was mapping onto this. Or maybe that was just like a title that was used kind of loosely. The second question, if I may, is slightly different. The function of the coils on the back and their interlocking and then reversing direction, yes. Lower to upper, were these slots cut into it?
Yes,
through which
they're cut through the plate. And there was the pointer design it's a little bit like, like an old-fashioned record player needle. Yeah. It has a little needle thing that rides in the slot
and slides
as
up
it
and down
goes
on
around. The idea behind these spirals is to make it possible to have a scale that's showing something like 223 consecutive months with space so that you can write something in each cell for each month. And so you, instead of going once around for 223 months, you go 4 times around with the spiral, and then the operator has to manually pull the needle out and put it back at the starting point. It's an idea that's a bit too clever by half. I think the operator would probably get sick of doing that reset movement after a while.
So it's not related in any way to the acanthus.
I don't think there's an aesthetic aspect to it, but if you want to see aesthetic aspects in the design, you're welcome to do it. But there is a functional point to it. The design was meant to bring. There's also the fact that it's divided in 4 in that case makes it possible to show also something subtle about the moon's motion, which I won't go into. So it's not an accident that 4 was chosen.
Thank you.
All right. We have 2 on the left and then on the right. And if you don't mind asking your question into the microphone, if you're comfortable doing so. Oh, yes. My left.
Thank you for a very nice talk. You mentioned a bit that on one hand you said, I think the whole mechanism was understood with all the gears, but you were not sure whether the planet motion, to what extent it would actually include the retracing and westward and eastward motion. So to what extent do we know that it sort of was correct with even their fault?
The part I said we have full understanding of, because either the gears still exist or the gaps are I won't say trivial to fill in. It took a long time for people to solve the puzzle, but once you've seen it solved, you know it's right. But that is the whole sort of moon-sun calendar module of it, which is that's the part that survives and accounts for every one of the surviving gears except a single one. There's, annoyingly, or stimulatingly, there is one gear by itself in so-called fragment D, which has, and that doesn't belong to it. And even when you fill in the missing gears, that 63-tooth gear doesn't fit in anywhere. So that in itself tells you there's something more. But it's also clear, and this is what Wright was seeing, was that there are all kinds of mountings on the front of fragment A that imply that there was something mounted there. There's a lot of space for a whole other module of gear work, and that's the planetary stuff. And this one surviving gear, unfortunately, there are about 15 different ways you can use that 63-tooth gear. So it's not, it doesn't help solve the problem. Some of the data in the fragment G thing you can use to narrow decisions, but it's an underdetermined problem reconstructing the planets. What has to have happened, though, to get backward and forward is you need to have devices that involve gears that are, say, have a peg in them, and there's some kind of a slotted apparatus that is riding on that peg from a different center so that you get speeding up and slowing down or even change of direction. And there is such a thing surviving for the moon. It doesn't make the moon change direction, but it makes the moon change speed. This was one of the, it was detected by Michael Wright, but he didn't figure out what it was. The AMRP group in 2006 figured out that it was lunar anomaly. And it's basically the verification that it really was doing irregular motion. So it makes it much more plausible that the planets were doing that too.
All right, thank you so much. Go ahead.
Oh, thank you for a wonderful talk. I guess, so just to probe a bit further, I had a question about your theory that the mechanism was didactic in some way. So I was curious, do you think both about, in terms of what we know about childhood or adolescent pedagogy in this period, if that would encompass enough astronomy for this to be, yeah. So
this is not childhood
not
education.
childhood.
No.
So
This is
yeah.
This is the elite philosopher's classroom for rich client pupils. That's my thought
so
for it.
so it's a wealthy merchant or aristocrat
well,
is.
It's also possible it could be
astronomer,
a rich guy's toy too. But I think if you really want to find someone who would want to have those things shown, it would be someone who wants to. It's prestigious to own it and to show it off, but also there has to be some context in which you would get meaning out of it, and it's in more like say continuing education classes than like grade 5 education.
Childhood pedagogy. Yeah. Okay. Thank you for the clarification.
All right, I noticed there are 2 questions. So the individual nearest us, you can go first, and afterwards you can ask.
Great question, by the way. Kind of following on that didactic, I mean, what would it cost to create this device? in terms of labor, in terms of materials, in terms of, I mean, the size is not that big. It's not probably meant to be shown to many people at one time.
Yeah, you could call it microtechnology. It's not nanotechnology, but it's microtechnology. You know, when you think about, you know, how you would get to the point where you've got this complexity there has to be a background not just of sort of building up from simpler prototypes that don't do as many things, but also bigger prototypes. You wouldn't start by making it with gears that are so small before you do them on a more convenient, larger scale. It's impossible to quantify the cost, but obviously this is something that would take, first of all, you need a team of people. This really is not a job for one person. You need a collaboration. There has to be somebody who can give the astronomical information that's needed. Somebody, it might be the same person who can do the mathematics to break down something like, well, for example, the calendar relation is equating 19 solar years with 235 lunar months. And to do that transition from 19 to 235, you need some sequence of gear engagements that's going to do the arithmetic for you. It's basically all multiplications and divisions when you do that. But you want to figure out how to do it. That lunar anomaly thing with the pin and slot thing, that's mounted on a gear that it's a big gear that you see on the back of Fragment A with 223 teeth. And that gear has been designed so that it does a very slow turning at essentially the speed of the motion of the moon's apogee around the Earth. And that's a kind of a side product on the way to the outputs on the back dial. So again, a mathematician or a mathematically minded person was in there. And then, of course, there are people who know about this kind of high-end technical metalworking, who I imagine are the same sort of people perhaps who would make medical instruments, or perhaps the actual instruments that astronomers used for observations, the sort of theodolite that Heron describes for doing surveying at the top end. You know, it's not just astronomical devices that need that kind of skills. Okay. So I imagine you've got a whole team of people here working for you for probably weeks. And the materials, yes, I mean, this is probably, you know, we talk about it as bronze, but there's more than one alloy in there. You can see from the CT that there are some really radio-dense metals that are not corroded for small components in there mixed in with the other stuff.
They had an understanding of
the material, you know, different materials good for different
those.
things. It looks like the inscriptions may have been on more like a pewter-like material than a bronze-like material. But we don't really have very good metal analyses for this, but it's clearly varied. So, yeah, I think this is an expensive object. Mind you, the ancient Greco-Roman world was full of very rich people who had very expensive objects of different kinds. Not many would choose to spend their wealth on this. I don't think there were ever lots of them around.
Right. Sorry, a bit of a follow-up. Have we found any objects that share any characteristics with this device?
That last vanished slide, I don't know what was happening there. I mean, but two or three of my slides just seemed to disappear into the ether. I could see them as the next slide, and then when I clicked on them, they just disappeared without coming on. So don't ask me. Anyway, one of the second last slide that you didn't see is the answer yes. We have there's a portable sundial from late antiquity, let's say around 500 CE, in the Science Museum in London. We don't have a good provenance for it, somewhere in the Eastern Mediterranean regions, which had a kind of gearwork attachment. It's not part of the sundial, which is to tell the time of day, obviously. But it's like, you know, on a modern Rolex, you have this little thing that tells you the day of the month while you're seeing the time of day from the mechanism. And you set it mechanically. Well, this would tell you, you would basically click it every day, and it would advance one day in the cycle of the 7-day planetary week, you know, Sunday, Monday, the day of Mars, etc. It would click forward one day in a lunar count, that's just a basic 29 alternating with 30 days lunar months, and something to indicate where the sun is roughly in the zodiac. So really crude. And this has been known since around late 1980s. It's actually what got Michael Wright interested in the Antikythera Mechanism, because he was the curator at the Science Museum to whom this thing was brought. And the other, I'm rather happy with this one. It's one that's been known since the mid-19th century. It's just a single sort of gear-shaped thing, but it has not been recognized as a gear. But it's a ratchet gear. There's a ratchet gear in the geared sundial, And this is almost identical to it, except that instead of 7 lobes on it, it has 14. So it gives 2 7-day weeks around the turn. And it is labeled with the 7 planetary days. So even though the rest of that mechanism is gone, once you see it for what it is, it's another like that. And again, we can't date it very precisely, but sometime in the Roman period. Otherwise, no. There are no surviving examples. And the descriptions in ancient literature of planetaria, only one of them actually mentions the word for a gear. Well, it's actually more than one word, a toothed wheel. That's Theon of Smyrna, refers to toothed wheels in the context of planetaria. He's the only one. Everyone else just blurs over how they work, which I think shows you that sort of closed box mentality. There may have been a literature that gave the technical specs, but we have no surviving hint of it.
Thank you so much for that question. I know there's a few members in the audience who would like to ask another one. I do want to be cognizant of the time. We have reception at 7:30. We might be going just a little bit after. If you didn't get a chance to ask your question, there will be time, of course, at reception. The next person in line will give you the floor for the last one. If I can ask both parties to keep it somewhat brief so we can have drinks and snacks. Go ahead.
Hi, I was just interested in the aspect of Aristotelian cosmology and implications that there is a cosmic order, even the patterns where Aries as Mars and these symbols are sort of reoccurring. Do you think ancient technology was sort of superior in that regard because it was able to capture these patterns, and our current technology sort of falls short because it's looking very much at the empirical level and not exactly trying to see deeper patterns of meaning that seem to be prominent back in the day? So.
You mean superior in a kind of moral sense or superior in a technical sense?
Technical, because it seemed to have an intuitive element to it, because it's looking at symbols, it's looking at these Platonic forms or whatever, and even Plato, his sense of using that wheel to explain his ideas. It's focusing more on the symbolic rather than the material. And it seems like most of our, even computers these days, they're very focused on patterns that aren't necessarily relevant at that intuitive level. So do you think there was probably something, even the Monday, Tuesday, the fact that these symbols are in our everyday language and in our everyday use, they probably had some precedence in terms of getting us towards deeper knowledge of some truth rather than what we have today?
Yeah, I wouldn't couch it in a language of superiority of technology.
I see.
But I do think, and this is one of the things that interests me very much about the Hellenistic period, I mean, pre-Roman Empire, Greek astronomy especially, is that there is a lot of the evidence we have is not about so much the sort of rarefied research end. There's some of that. But much of it is about the engagement of specialists with a broader public. There are inscriptions that were publicly placed. There are sundials that had inscriptions on them that explain the functions of a sundial. So you don't just know how to read the time, but they to some extent explain how they work. I mean, the popularizing literature survives better than the technical literature. So to some extent, this is because what the astronomy actually constituted at that time is just moving into becoming difficult for people who don't have a lot of mathematical education to understand what's going on. And you see when you look at, for example, Geminus's introduction to the phenomena, that elementary exposition of astronomy that I was mentioning, that it sort of skirts over what we know is going on about planetary theory at the time. You find out about it from later sources that are looking back. I think because it's just too hard for that kind of an audience to really understand what it's all about. It's stuff like epicycles and so on. But there's a lot which is quite intelligible. And so you get everything ranging from the whole tradition of the literature surrounding the poem of Aratus, which is all about the constellation pictures, to these inscriptions from Miletus that are about correlating weather patterns with the risings and settings of stars. And then there's a really strange one from Rhodes, maybe the same place the mechanism came from, but I think it's got nothing to do with the mechanism. But it was found again around the same time, around the turn of the last century, in a countryside site And it's an elaborate table of cycles of planetary motion. And why would you put that in inscriptional form? It has to have been meant for some kind of for people to look at and at some level appreciate. Maybe not understand all the technicality, but at least get some kind of a level of, even if it's just an impression of the complexity of the cosmos and the ingenuity of the human mind to be able to grasp it. I think there's that double thing that runs through a lot of this.
100%. But I feel like nowadays our focus is on the naturalistic element of that expression, but it seems like the focus on cosmic order prior to our everyday like empirical focus, like that kind of science seemed to still have like some aspect of trying to give to the public what they want, which is simpler knowledge in terms of symbols, that Mars is like Aries, for example. And do you think that our current progression in terms of scientific knowledge, it distances the public from that truth?
I think it does distance it from it. I suspect that most practitioners of modern science would say a good thing too.
Yeah.
I mean, what I was saying from Ptolemy, we know Ptolemy as being a highly mathematical, technical, empirical scientist, and yet he has this almost theological cosmology,
Exactly.
which seems so remote from what
We're
a
doing.
modern historian of mathematical astronomy values in his work.
Exactly.
So it is certainly very different. I just refrain from making a judgment call
Yeah.
about which is better.
Of course.
Right.
But thank you for answering
Thank
my
you so
question.
much.
Thank you.
Do we have time for one more? All right, we're going to take one more question.
I'll ask after that.
All right. Then I believe you had your hand raised early. You had your hand raised before. Would you still like to ask your question?
Okay. Thanks so much for that great talk. I don't know if this is a great question, but you just mentioned how Ptolemy's kind of own perspective or critique of the mechanism was that he didn't think it was expressive of, I suppose, these mathematical or these things motivating the actual motion of the planets in the way he studied them. So I was just wondering if you can comment more on, if the average user was using the mechanism, what kind of understanding would they have had about what motivated motions of these things, not in the mechanism itself, but in the heavens itself? What kind of explanation would they might have given?
The average user of the mechanism, I mean, I wonder how many people ever got their hands on one. We're probably talking about a rather small number of people, but I think it has to have been meant to be operated by someone who could give a narrative explanation of what's going on, I think. Those inscribed texts are meant to help with that. And I could imagine, for example, that those plates, which we talk about, I'm not entirely convinced they really were covers, but they were accompanying plates with text written on them. And they would be sort of the second best if you didn't have an informed operator to give you the whole running talk about what's being shown while turning the knob. You could leave it just sitting there, and you'd have these texts there to explain, well, this is the planetary theory built into this. This is the, this is the eclipse theory, and so on. But the text is not as good as the spoken explanation while you're actually running it. So I think a typical layperson finding this thing for the first time. Well, I remember what Cicero says. If somebody this is a De Natura Deorum passage. If somebody in barbarian lands like Scythia or Britain were to find a spira like this one that our friend Posidonius has, wouldn't that person grasp that an intellect must be behind it? That's not saying the person who finds it would understand, this is an eclipse prediction cycle, this is a calendar, and so on. No, but you'd know that it's something clever that a human being has made. So I think that's what a typical uneducated person would get out of it without a lot of hand-holding.
All right, thank you for the question. Dr. Jones, thank you again for a very informative talk and a very lively Q&A. I will hand it over to Allison Keith.
Thank you very much, Bree, for moderating the Q&A. Thanks very much to the Wiegand Memorial Foundation for sponsoring this lecture series. And most of all, thank you, Professor Jones, for a stimulating presentation this evening, joining ancient science and theology with a huge amount of modern technology to boot. Thanks so much.
Salute.